Hi, my name's Bob Greenyer. I've been talking to myself for the last 15 minutes. I didn't actually hit the go live button, so I feel a little bit of an idiot right now. Anyway, so I've got to go through everything I've just gone through, and let's hope I get it in the right order. Sorry for those that were waiting patiently, and thank you for waiting. Anyway, so we are here to talk about spectrometry, and this is in the visible spectrum, and this is because we need to see potentially if there are any transmutations going on in the supernova reactor. And for a long time I was hoping that I could use a diffraction grating like this, which is 1,000 lines per millimeter linear diffraction grating. And this gives you all of the many of the visible spectrum, and it shows here from 300 to 700 nanometers. Now, these are very cheap. You can get them on eBay for about, I don't know, $3 or something. And it seemed like quite a good way to go. And you build a little box and a slit and so forth, and you get the light going on your webcam or the camera inside your phone. And there's free software out there to use with this. The problem I was having was really getting a solution that would be able to look through these holes in the reactor, these holes down here, to see the reaction chamber inside. And you know what, I'll actually be quite glad to finish this experiment, because you know, having these around the lab, you get some funny looks. But anyway, so the reaction's going on in here, and we want to be able to look through these holes here to the reaction chamber and see if there are any changes in spectral lines. Now, what do I mean by that? Let me see if I can find that out for you. So here we have the spectral lines for elements in the periodic table, courtesy of Field Test Systems. And basically each element has a unique set of lines. And what this is if you know from your physics or chemistry or whatever, the Bohr model of the atom, the basic sort of, you've got a nucleus in the center and then a set of sort of rings of electron shells, so-called, around the nucleus. It's a way of visualizing it. When energy comes in, that can cause an electron to go to a higher energy level, and when it comes back down, it emits a photon, and the photon is observed as these spectral lines. And you can see there is a pattern for each element in the periodic table. Now, in the case of the supernova reactor, we're going to be starting off with residual moisture in there because it's got air. So you're going to have hydrogen, you're going to have oxygen in the air, nitrogen in the air, you're going to have carbon because we're putting carbon in there. There's also going to be a measurable quantity, I think it's 1.28 by mass percent of argon in air. And then you have potassium and calcium because we're going to be starting with carbon. And we also found some trace elements of sort of manganese and iron and so forth in the pencil lead, as it's called. It's not lead, but in the starter, which is used by Dr. Eagley as a starter for the production of the ball lightning, the dusty plasma, as he calls it. And so this was the process. And the question is, do we see other elements like titanium and vanadium? Do we see things like copper? And an increase in things like iron and so forth. Now, you could argue that, for instance, carbon could become carbon dioxide and then come out of the reactor, so you have a relative increase in iron that might be in there anyway, or that as the reactor gets more energetic, then you see iron being produced, or rather iron being excited or being lofted. The question is, do we see elements that should not be in there, and do we see specific elements occurring when we are running the reactor for a certain length of time, or when we are exciting it with a certain frequency or a certain intensity? And having the spectrometer looking into the reactor gives us some sort of metric of, okay, so are these elements being synthesized? And in the past, we've put it on an ADS, and we've looked to see, are they being synthesized? And we saw elements that one might expect from George Osawa, the guy that did the original sort of carbon rods together with a high current, just sparking them together and then seeing production of elements, sometimes underwater. It's these Osawa reaction chain. If we're seeing it also in the spectral output, this is another data point. And then further down the line, hopefully when I've had a little bit of experience with this and the data has been shared, we can use the same technique with the Vega reactors and maybe see more interesting elements being synthesized, because typically we're not necessarily starting just with carbon and air and a pencil lead. We might be starting with a range of elements, and you have seen us use tungsten, you have seen us use indium, you've seen us use brass, which contains lead and copper and zinc and so forth, and a range of elements are in there, and so there's more potential for other elements to be synthesized that could produce specific spectral lines. So that's what we're looking at there. Okay, so oh yeah, sorry, I didn't have a shave today. Okay, so what I tried initially today was this is the solution I've come up with, and if we go here, actually, it comes in a nice box. I don't have any relationship with Spectrix. However, I was looking for something that had a fiber optic, and most of the fiber optical systems are ridiculously expensive, certainly outside of our ballpark. But this seemed quite affordable, and it was worth to take a shot on it. And it's $399 plus shipping and taxes and whatever else it is to go to your region. However, Alan Goldwater tells me today that the two channels that he sells this through, which are eBay and Amazon, they don't have any in stock at the moment. So I'm sorry, but we're lucky that we've got this, and I'm sure that it's good that he's got none in stock potentially, but you will be able to see this in action and make a decision possibly when they do have some in stock. So I was going to use this light, and this is kind of like a vanity light for a car, and you get 4 of them, and it's a little controller here with a infrared type controller to switch the red, green and blue on here. And I was going to use this to demonstrate to you today how this works. And when I got it, it was like currently it was fading between the various colors. I thought that's quite nice because you can see some of the LEDs go up and down, but I really wanted to be able to switch between the red and the green and the blue and mixtures of them, which I know this allows me to do. But I couldn't find the right controller, and I found a controller, and I got it to actually do the control I wanted, the red, green and blue and fade, and that was great. But I accidentally pressed one of the buttons and it turned it off, and I couldn't turn it back on again. So I thought, oh dear, I've got to come up with another solution, which I did. I came up with the solution of using my phone. And first off, I'll show you the actual device here before I show you what I've come up to demonstrate it to you today. So here it is. It's very small. There's the palm of my hand. It has one port on the top, which is an optical port. You can maybe see that. And it has a micro USB, the sort that would go in a last generation mobile phone at the bottom. And the power and the data goes through that. And then at the other end you have your optical fiber. And this easily fits through one of the ports. And I'll need to make a gland for that. So if I go here, you can see that I can actually insert through this port here. Maybe you can see there, and you can see through, I can look. So I'm going to make a port. Now, one thing I learnt this afternoon when I was preparing for this presentation is that these LEDs are exceptionally bright. And that taught me that this will saturate. And so it may well be the case that we need to put an ND filter in front of this. I am considering, and I've thrown everything on the floor, I was already considering to use these wonderful sapphire windows that were provided to me by Jeff Smathers, who is oxyhydrogen researcher in the US. He sent these to me, and this will certainly do some protection for this and the optical imaging camera that we're going to be using. However, does sapphire, and this is something I'm asking you, maybe you can find it out, will sapphire affect the spectrum that we can see? It's normally considered a good material for light to pass through. Obviously it's high temperature and clear. But I will need an ND filter, it would seem, based on my experimentation today, so that this device isn't saturated. Okay. Now, I'm going to run through some specs before I show you a live demonstration of this. But before I get there, I just want to talk about what I came up with. So I came up with this. This is a sample container, and I cut a hole in it, and I've made effectively a gland, and I can insert this into that, and we will do that. And there's a piece of software that I actually purchased for use in Project Omar. Actually, I didn't purchase it. I established what I needed, and it's actually free. And you can go and get this piece of software. It's called SWIFTBIC. It's on Android. I don't know whether it's on Mac products, Apple products, but it's called SWIFTBIC, and it allows you to strobe the light. And this is when I came across the dreaded rolling shutter problem. So the reason I was going to use this was to monitor and freeze frame the vibrating plates of the Amasa vibrators. But I was testing it at home in early 2019 with a fan, a domestic house stood fan, and I was getting these horrendous distortions because and I was going through my cameras going, oh my god, everything's got a rolling shutter, I just cannot, it's not going to be useful data. So I had limited time to get everything ready, and so I pulled the plug on that. But I have the videos, but I didn't share them because they were just embarrassing demonstrations of rolling shutters. However, when I was thinking about my problem with my LEDs not working today, I thought, this software allows you, and I don't know if you can see this, you can actually choose a color here. Rather than making the backlight strobe, you can actually choose a color. So let's say we choose over here, this is a red in theory, and I press this one, it'll make the back screen of that, and it's actually a lot redder than it looks on this camera because it's saturating out and making it look more white because I've got the brightness turned up. Anyway, so we're going to be using that. But before I do, I just want to run through a bit about the actual product itself. And we have that on another tab. If I go to here, and I think we can go to here. So this is the actual website itself called Spectrix. I guess they're thinking about using it for astronomers, and a lot of people like to do this. And here we go. They're claiming 400 to 800 nanometer with an overview of 350 to 950. It does seem to produce some data even outside of that range in the data file that it saves. I don't know whether it's any use. They say 3 nanometer resolution here, 1.5 nanometers typical. And it's quite nice because the Windows software you'll see is extremely simple. It just, as long as you've got the device plugged into the USB 2, and it's only USB 2, it turns on and it just starts, you just set the COM and turn the device on, and you're good to go. And you can actually set it, and I'll show you this in a minute, to auto-save spectra. But okay, so that's all it really has on the site. But they have a PowerPoint presentation as well, and you can see some extra details here. So it is 16-bit but 13-bit effective. So that limits your number of points that it can do. So 400, 800 nanometers, as I said before, 350 to 950. It claims a wavelength accuracy of 1 nanometers typical, which is very good actually. Very expensive devices only achieve that. And they're saying the resolution with that optical fiber, so it's actually limited by this optical fiber, is 3 nanometers with 1.5 nanometers typical. The interesting point for me was the integration time. Now, they can do 10 milliseconds to 1 second, and it's like 10 milliseconds to 980 or whatever. I don't think they want the extra digits, but the 10 milliseconds, that worked quite nicely with these LEDs. And so it wasn't saturating, apart from I think it was on the green. The green is just, or one of them is just so intense it was still saturating. So I had to do that right down at the minimum. So I suspect that when we run the sapphire-like experiments that we call Vega, and we run the supernova experiments, because they have such brightness in them, that we will have to run this at 10 milliseconds. And the update rate there, you can see, is 120 milliseconds. And what this means is that it'll sample for 10 to whatever, and then it'll update in every 120 milliseconds the data. And what I found is when I turned it on to autosave spectra, that I was getting, I would imagine, a good number of, like in 1 minute I was getting 350 samples put down, and I had it set to 10 milliseconds. What I'm going to show you in a minute is I've set it to 120 milliseconds because the intensity of the light is much lower, and so I have to sample for longer to get a smoother waveform. Okay, so that's that, and the reality is that I will probably do what they've done here. This is a thermal light bulb, so I assume that this is something like a tungsten filament light bulb, and this is a fluorescent light bulb, and I can attest to seeing something similar to this in my testing of a fluorescent light bulb in the last couple of days. And this is quite interesting because a lot of people suggest using a helium lamp and maybe a hydrogen lamp or a krypton or neon or whatever to do calibration. I actually thought to do just LEDs, and you can go and easily buy and affordably buy LEDs, discrete ones like this one here, which are a specific nanometer. But even better than that are lasers, and lasers are very specific nanometers, and they're quite affordable to get just very cheap lasers. And so I would probably look to do the calibration of it using a number of lasers, and so they've got a green laser pointer here and a red laser pointer here that they've used in their experiments, and you can see it lines up quite nicely with their claims. Okay, so let me get this together. Is there any questions at this point? Okay, so I'm going to show you this. And like I say, it's quite satisfying to put to insert this into here. I should probably not get so much pleasure out of doing that, but I do. And what I've got is I've got it looking at a part of the screen where there are no sort of other instructions for the Strobely program. Okay, so it's you can see there's a little black, maybe you can't, I can get the angle right, there's a little black area there, so that's going to sit down on that area, and we can put that down there. And what you can see right now, as I close this off on the live feed there, is just noise. That's just noise, and it just goes to show what these how good these Samsung displays are. So I'm going to put this into shot here. Now the reason I've got the white paper in the background is so that the webcam up here that's looking at it gets the white balance right, hopefully, and that will give you a better idea. So this is actually cyan that's here. Now I'll bring the strobe, the actual device, here in the background. Okay, so what I can do is I can tweak this and I can change my color. And at the moment, in the area that is being captured by the optical fiber, it's only seeing black. But if for instance, if I go to red over here, like just before it kicks to white, so it just, okay, so that's red, and I hit torch on the bottom left, it gives out a red line, and there we go. Now, to make things nice for you, I've taken a graphic from Britannica, Encyclopedia Britannica, and I have overlaid it on this chart so you can see what should be there. And it's not on that frame, it's that on that frame. So you can see that when I'm looking at this with my own eyes, I can tell you it's actually quite orange. So the webcam up here is picking it up as red. but is actually quite orange. So what you're seeing actually fits that better. So let's change the color here. I'm going to change it to a deep blue here, and I'm going to turn that on. And there we go. It's down in the deep blue. Interestingly, you will see that if I go over here, you'll see that in the sort of, even above 900, it's seeing something here. Now, this would be in the sort of infrared area. So one thing about blue LEDs, they were very hard to achieve. They were the last LEDs to be effectively made. And it might be that they, typically well, certainly the ones that I've used in the past, they required more power to drive them. And so you could imagine that they would run hotter. So this actually might be heat, IR, not visible, but IR that's coming out of the blue LED that's producing this blue look here. Okay, so can everyone see what I'm showing there? Just want to know if everyone can see what I'm showing. So hi Brian, thanks for joining us. Hi Gardy. Okay, hi Dan. Right, so I'm going to try a few more colors. So again, I've got this thing here, this one here, and I can turn this spectrum, color spectrum on and off. And so I'm going to choose a different color here. So we turn off the torch, and it's reporting black, so we're just going to see noise. And I'm going to choose a good strong green here. I'll turn on the color chart again, and I'll hit the torch, and what do we see? Well, there we go. It's right in the green. Lovely, lovely. So this is not reporting the right color. I can tell you with my eyes that what's on the screen is green, and in fact it's better when you see it there. In fact it's not now, but if I go down here, let's try a sort of a yellowy color, okay, and turn on the torch. Now you see how it's making the yellow there? It's mixing the green with the reddy orangey color, okay? So it's actually using color theory there to create our yellow. And when I'm looking at this screen, it really is very yellow, this screen here, to my eye. Okay, so it's achieving the goal there. Okay, so that's about it, really. It's a short one tonight. Let me show you some aspects of the software. So there's this thing called autosave spectra here, and if I click on that, it'll start saving spectras every time it does a sample. So at the moment, it's every time it's an update, it's every 120 milliseconds, it's saving. And I'll show you the format that it saves that in if I can arrange it on the screen. This is quite good because it's just a standard CSV file, and you can concatenate those with the timestamps, and you would have a data feed. But it actually has Python scripting, so I imagine that you could use Python and capture that into a database or whatever, and then you could show the progression through a timeline alongside a video of the experiment operating, and also maybe sync that with sounds that are going on, and sync it with voltage and current being used, and also with any potential radiation emissions being observed. So when you have multiple sets of data together, you can learn a lot more, let's put it like that. And so if I actually change the integration time here, you'll see it becomes a little bit rougher. What I will say is that when I was using these bright LEDs, these ones here, these bright ones, the 10 milliseconds was more than enough to get a very clean spectra. And so, and that was true of when I was looking at the reverse side of the camera, the phone, the actual white LED, seeing that spectra that I've published on the title frame of this presentation, and that was much clearer. But you can even see that the 10 milliseconds, you are getting the two colors there that are making up this so-called yellow. It's the reddy color and the greeny color LEDs that are making up the yellow to the eye. And so even at 10 milliseconds, we're getting useful spectra out of this. And I'm not sure that I'd ever been able to achieve that using webcam solution. It just wouldn't have done that. Now the boxcar width here allows you to smooth effectively. It's reducing the resolution but giving you a kind of like softer look at what's going on, and this might be all you need to get an impression of where the light colors are. And I found that actually this was one way you could partially solve the clipping, but really it's losing a bit of data when it's clipping, when it's too bright. And so if I actually change the integration time here up to 120 again, you end up with a very smooth curve. And so that's really showing. So I'm going to switch to black, and you can see that drops down to very low count numbers. And then I'm going to change to, let's try some purpley color like this. Some purpley color. What do we see? There we go. So we've got some blue and red in there. And this is really, really purple to the eye, but it might be an angle actually. It might be an angle thing with the CCD on the webcam that's making that look blue. But I'm telling you, this is purple. Maybe you can see it's purple. No, you can't even see it's purple there. But anyway, it's purple. I'm telling you it's purple. It really is purple to the eye. And so this really is delivering what I would have hoped it to do. Is the 10 millisecond minimum sample time enough to get us what we want? I think it may be. I think it may be. And the beauty of this, just as I am showing you right here, this window where I am showing this device, this could actually be a video of the reactor, and where my ugly mugshot is here, this bit here, this could be other data panels in the live recording of the experiment. And so you can already see how we can share multiple pieces of data in the same frame and have it all synced together. So is there any questions? I think that's all I want to say tonight, really, unless you've got some other questions. It comes with a USB stick with the pieces of software on there, and plenty of space to chuck lots and lots of data if you so wish. And it comes with one sample chart, which is actually the piece of paper that I'm using under here. So it's like it's been verified. Okay, so have you got any questions? I'll change the color. Let's change it to something purer. Okay, this is a cyan. Let's see what that does. There we go. It's got green and blue. Well, it would do. It's cyan. Now it looks more blue on here, but not on the screen. It's cyan. So when I bought this on Amazon, and it's from California, it's from the Bay Area, you paid extra. I can't remember what it was, but the device was $399, then you paid tax and shipping and import duty. But they were very good that they bundled everything together, and it was like I think Amazon's global shipping service, and so everything, all the tax that you would pay into your country is already sorted out, and so it was like pay one figure and then it just turned up. I was very impressed, and so not only was it simple to acquire, and thank you again to Bido for making that happen. It's very, very simple to use this software, and in fact the software that you're looking at right here is probably all you'd need to do most things. Okay, can it use different sensor for full spectrum analysis? I need to see it all. Well, the reality is that spectrum analyzers like this, they tend to only, the broader the spectrum you want to look at, the less definition you often get. And if you look at some of the more expensive devices, which not necessarily better than this, by the way, they tend to shift one way or other and have a smaller spectrum. So in answer to your question, if you want good quality data and you want a wider look, so more down into the UV and more up into the far infrared, you're going to have multiple devices, and there are people that sell these multiple devices. Secondly, if you want to be looking at X-rays, you don't want this kind of device. You want a scintillator, and like we already have that, or something like an X123, which is able to look at really soft X-rays with, I think it's a germanium pin diode or whatever. But those devices are not cheap. They are really expensive, and fortunately, I think Alan acquired one secondhand, and you know, so it is possible to get something cheaper. But this is an order of magnitude and then some more affordable. And you know, if you're not trying to do things to the 50th, you know, decimal place, I think I've already demonstrated with this simple experiment showing using a C.I.C, whatever it is, the LED, the Samsung, whatever they call them. It's not an OLED on this, but it's their own thing. I've shown you that the spectrum that I see with my eyes is the color that it is finding when it's doing the real-time detection that I've shown you. So if we can get to a situation where we are able to, in 10 milliseconds, take a sample that allows us to see spectral lines, and we see those spectral lines shifting in the course of a supernova experiment or a Vega experiment, then I think this is extremely valuable data. And I know the Sapphire team have used this technique to assess the potential synthesis of elements in their experiment live. I would imagine that their device is a lot better than this device, but you can often achieve 95% of the answer with something that's a lot more affordable. And sometimes you can actually do better with something that's appropriate for the reactor that you're working with. And I was talking about this the other day. Yes, you can spend $10,000 on a CCD that's probably not going to be able to do as much with as much control as a second-hand 300-pound camera from 3CCD camera from the early 2000s. So, you know, it's about thinking smart. We aren't these big labs with big budgets. And I think these kind of solutions are very, very powerful. So in short, no, it can't use, it does what it does, and it's designed for the optical spectrum, and it's actually quite a broad one, as I show you here. It's that's the optical spectrum there from the sort of violet, and it's going down into the UV, and it's going up into the far infrared or near infrared. I wonder if it's possible to run a probe in front of an old Vega Nova run videos for any possible data. Maybe if they were taken with 10 or 12 or more bit video and the video display unit was showing that, maybe. But no, I would suggest no. I would no. This, you know, sometimes you just have to have the right tools in the right place, and sometimes it takes a long time to get an experiment together, and I wasn't ready to waste my time until I had an understanding of how to shield myself from the radiation, and a way to capture the spectra so that the data can... It's not always that the data is immediately obvious what's important in there, but you need to capture it when you do the experiment, and that might give you a clue. Let's say we see some particular transmutations, then people could say, well, that was just contamination. You say, well, hold on a minute. You know, this concentration of these elements in the ash correspond to the transmutations we saw in the spectra, and so, you know, you have extra supporting evidence there. Yes, there is software to determine what elements there are. If you go to the presentation, the PowerPoint presentation here, you can see that if you have a very specific line being produced, then it will produce a very, very sharp signal. So if we were to, for instance, produce sodium, let's say, for whatever reason, we were producing sodium, you would have this very strong line here. You know, so certain elements produce very good signatures. In previous LENR experiments, we've observed production of gallium, and if we produce gallium, there would be this very intense red line here, and so forth. So, okay, so californium has a similar kind of line there, but I really hope we don't see any californium, to be perfectly honest. Yeah, so like for thallium, I don't want to see any of that, but that's got a very discrete line, isn't it, here? So sorry, I'm on the wrong thing, so you can't see where I'm waving the thing around. So here's the gallium with the very strong red line, and here's the thallium. Aluminium has this strong green line here, and so that is one of the elements that gets synthesized in the Osawa reactions, and it would appear that we observed that when we did the experiments in a good few years ago with the normal NOVA reactors. So maybe we should be looking out for this green line here of aluminium, and that would be a good one to look at for real time. And so how would that translate to this? Well, you would see something that would be probably a lot tighter than what we are seeing here. This area here is the green line. In fact, this has some software, and you can actually move the pointer around, and it gives you a better idea of where you are focusing. So it's this kind of a 10. This is 480, 490, 500, 510, 520, 525 nanometers here. If I switch that to green, let's see if we can get a nice green here. There we go. So that's almost bang on the 520 nanometers. So you would expect to see this kind of green line from the aluminium. So, you know, there are potential chances for us to observe in the supernova reactor the synthesis. Now, you wouldn't imagine too much aluminium being in the charcoal, okay? And so if we find it there, and there are paths to aluminium in the George-Ohsawa reaction tree, so it's 27, so you know, nitrogen is 14, isotopes of carbon, maybe isotopes of carbon and nitrogen make the aluminium. Okay, so it has gone past curfew. How about isotope changes? No, you will not see isotope changes with this. The thing about an element is it doesn't matter how many neutrons it has in there. It's the protons and the electrons that determine what the element is, and they have this relationship between the protons and the electrons, and the electrons fill the shells relative to the element that they're in, and then they have these transitions which are the same for each isotope of the element. So this is really looking for instance, in the supernova reactor, I would be looking out to see this production of a green output, maybe for the production of aluminium, which shouldn't really be in any of the reactants. It can guide you. So, for instance, in the case of aluminium, you've got a problem because it's just one isotope. However, if you're getting synthesis, for instance, of more calcium, so let's go back to our chart here. Oh, it's come off now. The great thing about masking tape is it doesn't stick so well. Not masking tape, this electrical tape, it doesn't stick so perfectly, but that's good because I can get my phone back. Okay, so there's our green. So if we're seeing this aluminium line, where is it here? This aluminium line, that shouldn't be in the reactants, and but unfortunately it only has one isotope. But if I come out of this and we see calcium, you can see that calcium has multiple lines, and that the calcium has several isotopes. So if we see an increased production of calcium, we could then consider doing some isotopic analysis using a different technique, because we think we might have created some calcium, and does it produce a natural proportion of ratio of isotopes. Okay. Okay, so I think I'm going to call it a day. Thank you very much for your time. I'll just do another couple of quick color changes here. So this is a real strong orange down here. Okay, it looks really orange. It looks red to this camera here, but it's definitely orange. And I'm going to bring that up to more yellow. So this is a more yellow. And I'm going to bring that up to a green. We've got the green there. And I'm going to bring this up to this sort of light blue here. Kind of, this is more blue. And then we're going to go for a dark blue, really dark blue. Down there, and then a sort of pinky mauvey colour, and then kind of orangey reddy colour, and then we'll go to the white. We'll go all the way to the white. And we'll see here. There's the white. So you can see the RGB producing the white on this display. And I think that's quite nice. That's about it, really. So thank you very much. I'll try and maybe do another one on Sunday night. I haven't decided quite what I'm going to do it on. But there is I need to fill out the blog from the last presentation, and there is another video which has some really superb features going on. And I want to break those down and comparing them to things that principally Ken Shoulders saw. So thank you very much for your time, everyone. And sorry about me talking to myself for 15 minutes at the start of the video and not realizing I'd gone live or not. So I will say sayonara, dobry noc, do svidania, buenas noches, and I'll see you later.